Alrighty, so we're doing the BFS for coin change. In this particular problem, we are going to do a BFS at each layer of the coin change of our tree that we showed earlier. Let me reiterate the tree. So let's say we have 1, 4, and 9. So each layer of the tree is 1, 4, and 9, and so on and so forth. And it will go to the bottom of the tree before, whether we can everything goes past a 0 or hits a 0. If we hit 0, then we return the layer level. And if we never hit 0 and we have gone through all the coins, then yeah, and we've passed all the amounts, then we have returned -1, and that's how we do the BFS problem. So let's get started by setting up a queue. And yeah, so Q is equal to DQ. Yep. And we're going to append the amount and level. So 0 and amount and 0. This is amount. This is our base layer. So once we get to the bottom layer, amount will be equal to 0 and layer will be whatever layer it is. So let's quote remainder and we're gonna look at the layer. So now with that set, we can set the visited so that when we visit this, it catches the amounts that we have been to. And if we have the amount already, well, we can skip that. We already have that in our database, and we don't need to access that layer anymore because it's going to be the same result either way. So we can pause on that layer. On that item, because another item is processing that particular amount already. So what we're going to do add first to our visited is going to add amount. Why do we need to add amount is because we're going to be there already, and yeah, we don't need to process that anymore. We're processing it. So while q the current amount, the remainder, and the layer is equal to q.pop left. And with that, if if the remainder is equal to 0, we're going to return the level as we have just said. Otherwise, we're going to run this code here and work through each coin. For C in coins, we're gonna do if remainder minus the coin is greater than or equal to 0, and the remainder minus the coin is not in visited, then q.append the remainder minus the coin, and we're going to go to the next layer plus 1, so that we hop into the next layer. Then visited dot add our current amount, so we don't access that in another layer. So we're going to return -1 if we don't find it after we process all the coins and get to the bottom if everything passes the maximum amount. So by running it, layer, okay, let's run it again. Run it again. Okay, everything's good. Let's run it. So one thing that we could have done better is this variable is used many times, and so we can set that as next new remainder, and that's going to be equal to that, and we can replace all of these items with new remainder. Let's run it and submit. So this is beautiful. This formula, not formula, this algorithm is very beautiful, I believe. It's because the thing is about this problem is that it really gets us the it only access the layers that are necessary, the amounts that are necessary. So it gets that O of like n time, and at the same time, it is also cutting everything short because we're not doing DFS anymore. We're doing BFS. When we're doing the dynamic programming in the bottom up or top down, this is a DFS. We're bottoming up from 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to get to 11 or whatever number we're trying to get to. And the bottom up as well, where this is a DFS. This is exactly what it is. We basically converted our DFS, this one right here, into a bottom-up approach, which is also DFS. On the other hand, this particular problem only accesses the layer of the tree that works, and that's not repeating. So it allows us to be so much faster because we finish once we found the first item. In the other method, we don't finish when we find our first item. We don't even know for sure that I mean that's the one with the least layers, because I mean we could get two big numbers and not use a small number, all these small numbers to get to our amount, and so yeah, it's like this is so much faster in that sense. I think this is the way to do this particular problem. It is also using dynamic programming because by dynamic programming we are storing our visited and making sure we don't do that work anymore. We don't need to do that work anymore. And this is a different way of thinking. It's great. I think this will definitely earn you a lot of brownie points when you interview, because this is just so unique for this problem, and at the same time it is so elegantly like efficient. With that, I think we have thoroughly understood the coin change problem by doing this top down, bottom up, and the BFS method, and using dynamic programming. And I hope you enjoyed this series. If you learned something, please like and subscribe. And if you want more videos, check the link in the description below. Thank you very much, and have a good one.